the miniature zoom device, and then smart skin. SMA can be used for smart skin in case of aerospace devices. These days, have done Mangalan. If you see the video of Mangalan, if you go to the site of ISRO, you can see the actuators. Or if you see that movie, that Mission Mangal, then also you can see the way they have made the actuators so that it can change the shape and size while we are actually it's propagating towards Mars. So this is very, very interesting domain, I think. And you see that SMA material is used not only for medical surgery, it is used for other purposes also, like teeth. While we are willing to put the teeth in a proper alignment, when we are willing to make our bending of our spinal cord, etc. So this is the thing. And there is another important sensor that is called eye glucose sensor. So here, those who are actually, how to measure the glucose inside from our blood. How to measure? There is a device called AcuCheck. So each day morning we have to punch our fingertip, and from there we have to take one drop of blood and we have to check the sugar level. Instead of doing that, those who are wearing contact lenses, this type of smart sensors can be embedded inside the contact lenses. So what will happen? It will also detect blood glucose, body glucose from tears. And then there is an antenna. It will send the data to doctor's end or the patient's end. So instead of doing pinching of fingertip, you can easily measure body glucose by using this type of smart sensor. Another very important sensor, a smart sensor these days is SAW sensor, that is surface acoustic wave sensor. So here I am showing surface acoustic wave sensor for detection of biological parameter. It is recently used for measuring COVID virus. This type of SAW sensors are used in rapid test kits. But these SAW sensors are there in your mobile screen, touch screen, or your laptop screen. SAW sensors are using in mobile phones, in mobile base stations, mobile towers. As bandpass filter, these SAW sensors are very, very important. These are surface acoustic wave sensors, and they are having this type of interdigited sensors in case of transmitting end as well as receiving end. Then these days people are working on imaging sensor, that is for retinal prosthesis, MEMS sensor, artificial eye. So still there are a few challenges with this type of MEMS devices. Now I will directly come to our work that we are doing for last 10 years, I suppose. So before going to IISc, I have started working up just after my master's. I started working on MEMS piezoresistive sensing, that is pressure sensors are very much popular with piezoresistive type sensing. But problem was that those days in year 2005 or 2006, nowhere in this eastern region MEMS was actually considered as a subject. So I didn't get proper guidance. I had to move IISc Bangalore. And after returning back from IISc Bangalore, I started working on capacitive sensing. So first I'll show you there are 2 or 4 types of piezoresistive pressure sensors. And then I'll show you 4 types of capacitive pressure sensors that are we are mainly using for different types of biological measurement of biological parameters. So first, I'll show you the piezoresistive pressure sensors. Here you can see 4 different types of piezoresistive pressure sensors. Among these, 2 are square type and 2 are circular type. This is a very thin diaphragm, and the piezoresistive wire is deposited on the top of the diaphragm in these 2 cases. And in these bottom cases, you see that the piezoresistive wire is embedded inside the diaphragm. So this is a pressure sensor. After fabrication, it looks like this. But the fabrication technology in case of embedded and deposited are quite different. Those who are aware of fabrication technology can easily point out what are the differences. Then we have studied like parameters like potential, pressure dependency. We are applying pressure in megapascal, though this is 10 cos 10 micron diameter, but it can handle pressure in megapascal that is quite high. And this is the potential output in terms of millivolt. But after a certain time, we have to move from piezoresistive to capacitive, because we know piezoresistive resistance is actually dependent on temperature. So we have to move, if we go for piezoresistive pressure sensor, then we have to use some heat sinks in case of elevated temperature. And in case of and in other problem with piezoresistive sensor, that its consumption of power, it actually consumes more power compared to capacitive sensor, which is an addressable issue in case of wireless application. These days we are using these sensors for IoT, that is Internet of Things purposes. So we are willing to make all sensors wireless type so that it can talk to each other easily. That's why we have moved from piezoresistive to capacitive type. So first thing I'm willing to show you names capacitive sensor for measurement of respiratory rate. As we know, respiration rate is actually one very vital sign for human being to know whether a person is alive or not. And it is actually number of breaths a person takes per minute is called respiration rate. And the normal human being, adult human being at resting conditions, means while sitting or sleeping or resting, takes 12 to 16 breaths per minute, and the corresponding frequency is 0.2 hertz. So what are the other methods that we are normally employed for measurement of respiration rate? Number one is physical virtual observation, means when we are running, our chest is coming up and down. So through visual observation, we can easily understand, see that dog is actually sleeping by roadside, whether it is alive or not. We are trying to visualize that whether its chest is coming up or down or not, like that. Then impedance pneumography, that is normally used in lab diagnostic centers, acoustic sensing, fiber optic sensing. Then RIP. RIP is another very popular method that is using in laboratories, that is respiratory inductance plethysmograph or nasal prongs, etc. that I'm showing. So respiratory inductance plethysmograph, RIP method, is very, very popular in diagnostic centers for measurement of our respiration rate. But one thing we have to remember, that all these things, this RIP method or fiber optic sensing, these things are actually measuring respiration rate as a particular instant of time. This is the photograph of RIP. You see there are 2 inductive coils, one in chest, one is belly. So when we are inhaling or exhaling, what is happening? Your chest is coming up and down. According to that, the mutual inductance between these 2 bells are changing. So by measuring the mutual inductance, it's actually calculating the respiration rate. But everything depends actually measuring a respiration rate at a particular instant of time. Frequently, we are studying in the newspapers that a person expired during sleeping due to sleep apnea, because there are different types of COPD diseases or like brodypnea, tachypnea, podypnea, like that, where the respiration rate comes down beyond 12. That is called brodypnea. That is again abnormal condition. CRPD, and this is COPD is called trachepnea when respiration rate is very high, like fibrosis type of diseases. These days people are saying that when COVID is going, still there is some lung problem. It actually shows some symptoms of fibrosis or some asthma. Those who are having asthma, chronic bronchitis leads to asthma. So then there is some breathlessness. They are taking frequent breathing, but oxygen is not coming into the lung properly. So in case of this type of diseases, we need to monitor respiration rate at a constant level. Suppose in case of a normal human being like us, if there is a breathlessness, we can take inhaler. But think of a person, elderly person, who can't take inhaler by himself, or who can't communicate with others whenever he is actually suffering from breathlessness. Similar thing may happen for a kid or child. He or she cannot communicate with his or her parents that there is a breathlessness type of thing. So we have actually embedded the sensor. It is again micro sensor, smart sensor. So it is embedded inside the mask, oxygen mask, and it is just placed beneath our nostril. So array of sensors are there. So when there is abnormality, it will give signal to doctor, nearby doctor, or it will actually suck air from outside, as we have made one system based on this respiratory rate monitoring sensor. So this is the final sensor along with the signal conditioning circuitry. This is the performance analysis. Similarly, we have developed capacity pressure sensor array for measurement of heart rate. So here we know that abnormal condition of heart rate again is very crucial symptom. Bradycardia or tachycardia type of diseases may happen, and we know a normal human being pulse rate or heartbeat is between 60 to 72, and the corresponding frequency is 1 hertz. Again, heart rate is again very vital signature for human being, and there are methods for measurement of heart rate. One is by touch sensation. What we are doing, we are putting our fingers in the radial artery and we calculate the number of beats per minute. Another is optical plethysmograph that we are using in ICUs or in hospitals. But the problem is that in case of EPG or optical plethysmograph, there is a light emitter and light sensor. So light emitter is always on. So power consumption is much high than compared to a normal sensor, because light emitter or light source will also consume power as well as the light sensor. So in order to minimize that one, and at the same time your finger, one of the finger is blocked with the sensor, so you can't use that hand. So in order to minimize this problem, what we have done, we have made array of capacitive sensors, and the size of this array is like a circular banded, and we are putting it on the radial artery and we can easily calculate their pulse rate. Then these are the characteristics, these are the mask and top view and bottom view. performance analysis. Third one is the development of a power efficient hearing aid using microphone, MEMS microphone. So we know that normal hearing aid looks like this, and anybody who is wearing hearing aid, we can easily identify that the person is having some hearing loss or partial hearing impairment type of thing. At the same time, if your near or dear ones are using hearing phone day by day, you can easily understand that the cost of battery is very, very actually high compared to the cost of the device. So it is quite difficult to purchase such costly batteries each and every month. So we are willing to give a solution. Instead of these two microphones in the hearing aid, we replace it by MEMS microphone. So the power consumption of the microphone will be less. And this is the sensor after design. And this is the output performance of the first prototype. Noise is too much. This is second prototype. Noise is reduced in the audible range. And this is the third prototype, noise after third prototype. This is size is also reduced as well as noise. So we have international collaboration with IntelliSense USA, and they actually support in-house research facilities. And I have national collaboration with my parent institute, IISc Bangalore, through INUT. So this is, we are in Fab Lab of Bangalore. And this is another work I am willing to show you. Here we have used AI, that is non-pathological assessment of blood malignancy using microcapacitive sensor. So it is a non-clinical scheme, and instead of going to laboratory, we are willing to develop such a small kit so that to 1 drop of blood. Hello, time is over. Hello. With 1 drop of blood, this sensor can detect actually there is a display. The color of the display will change with red, green and yellow. If it is red, means all the cells present in the blood are all malignant. If few cells are malignant and few cells are normal, then it will give yellow. And if all cells in the blood are normal, then it will give green light. So instead of going to diagnostic center, one can detect this thing by doctor can detect, or these medical professionals can do this by using a kit. Even in case of a block level hospital or village hospital. So our motto is too small. We are willing to make a kit type device that is lab on a chip. No pathological lab condition is required, and it is portable, so anybody can carry it, and it is cost effective also. So this is the overview. It is 1 drop of blood, you'll get this type of thing. So this, if cell and then permittivity or sensor output is within this range, which is all cancerous cell. If this is between this, means few cells are cancerous, few cells are normal. Beyond that, all cells are normal. So these are the background study. So what we are doing till now, people are actually detecting cancer or malignancy through biological parameters. How come? They are actually monitoring it through microscope, whether there is any shaped biopsy, that is whether there is a shape or size change of the cell, its thickness of the cell has been changed or not, diameter of the cell has been changed or not. So significant changes actually comes up at a certain period of time. But here we are willing to detect the abnormality of cells in terms of electrical parameters like dielectric permittivity or conductivity or impedance. So the significant changes comes from initial state. So in first stage cancer detection can be possible by using such electrical parameters. We can claim. Then for doing this work, we have to do electrical modeling of WBC because we know in case of cancer there is a abnormal growth of WBC inside our body. Then these two works actually, this hearing aid and this cancer kit got BIRAC Srishti Appreciation Award in 2017 from DBT, that is Department of Biotechnology, and BIRAC is Biotechnology Research Assistant Council, and we are acknowledging Semiconductor Laboratory ISRO because we are having a MOU with ISRO for they are helping to fabricate this sensor. You see the array of sensors, and this is a sensor. Within it, there are 1,000 sensors inside this portion, this white portion. And see the size after packaging, and when we make the terminal ready, this sensor is ready for measuring blood cancer. So you see the size of the sensor compared to Indian 2 rupee coin. And this is the implemented device. As I told you, when all cells are red, all cells are actually cancerous or malignant, then this LED becomes red. When all cells are normal, it becomes green. Here my students are doing, this is the circuitry. So we have used IoT and AI also. New paper will come, I think within this month. This is already accepted for publication. It will come in the IEEE Transactions of Instrumentation this month, where we are showing that ANN-based cancer detection by using this sensor, so that it will detect what are the faulty data, when we'll get the faulty data, and what are the accurate data. So through ANN, it can classify those data. So this is through IoT, doctors' own, doctors' console, this type of data will come. So this is normal output and this is cancerous output. So from the difference, you can easily identify. Then when we have started this cancer kit work, we have visited all the block level hospital or visited all these village hospitals. We talked to the doctors. Then doctors told us that even these days also there is no some pathological lab available in the block level hospital or village hospital, so that normal blood count is possible. As you know, for any disease, doctor will ask for blood test, or doctor is always suggesting for blood testing in each regular period of 6 months gap. So that is called complete blood count test, means how much RBC, WBC and platelets are there in your blood. If there is any abnormality that leads to some diseases. So that complete blood count, that CBC count is very, very important. So even today there is no such device available in those block level hospitals or village hospitals. So for for a simple blood test, the patients has to come to nearby town or city in the diagnostic centers for doing the blood count. So we have started to develop such a device for counting blood cells by using microfluidic type of device and using dielectrophoresis technique. Here you see that we know that inside our blood, WBC, RBC and platelets cells are having different diameters. So in the electrical field, according to their dielectric constant or charges, they are actually taking different paths. So from there we can separate them to an electronic circuit is used to count what are the number of RBC, WBC and platelets are there. So this is our main objective, that CBC test on a kit, because normally in a diagnostic center there is a huge desktop device called hematology analyzer that is requires chemicals, lysing agent, protein marker, etc. For measurement of complete blood count, and it requires always diagnostic center. So our objective is we will make a kit type of device and it will detect anemia, malaria, leukemia, etc. That is the common diseases, and it is portable so that doctors or nurses can carry it wherever it's required, and it will be cost effective, affordable, so that anybody can use it, and no prerequisite knowledge is required to use such device, means anybody can use it. So we know with blood cell count, different types of diseases may happen. So here you see that if there is a deficiency of RBC, then anemia, kidney malfunction, lungs disorder, anything can happen. In case of lacking of platelets, it may be dengue, where there is a bleeding and clotting disorder, hemoglobin, less hemoglobin indicates anemia, dehydration, malnutrition, etc., etc. So these blood cell counts are very, very important. So this is the working principle, that we are applying positive and negative voltages in micro device, so it's not beyond 3 volt. So when the blood sample is passing the electric field, they are actually following different paths according to their sizes or their dielectric constant. So you see, this is the biggest size particles are the WBC, then RBC and platelet, and there are some electronic circuitry counters. So we are counting how many cells are passing. So RRCAT means Raja Ramanna Center for Advanced Technology Indore, that is an autonomous center for atomic energy of India, government of India. You see the size of the device is 1.5 cross 1.5 centimeter. So it is, anybody can easily carry it, and power consumption is less and less material is required, and we are not using silicon, we have used PDMS material, low cost material, so it's very much cost effective. And this is the device after fabrication. Now how much time is left? Another 15 minutes, okay. So I'll show you few prototypes that we have developed in our lab. And if you have any queries regarding this, you can write me. This is my mail ID. Okay. So first thing is the electrical impedance tomography, and it is these days we can use AI in it, so that it can be used for hand gesture recognition also. If you see these days, Google has used EIT for hand gesture, for recognition of hand gesture. Anyway, I think you have heard about CT scan. CT scan is computed tomography. That is very costly and it is not good for human health. So doctor always suggests that there must be 6 months gap between 2 consecutive CT scans, because lots of X-ray sources and detectors are used in case of CT scan. And at the same time, you have to visit to diagnostic center, and it is very costly. Those who have enjoyed CT scan, I think they can tell you that how much costly it is. And so in order to actually give a solution of CT scan, we are working on electrical impedance tomography. And now the question is, what is difference between tomography and X-ray? Why we are looking for tomography? X-ray is a two-dimensional thing, but tomography is a three-dimensional thing. Means it can take pictures slice-wise. Tomos means stones and graphy means pictures. So it will take a slice of your picture of your body, so that if there is a stone or if there is any lump inside your body, that can be easily observed by using tomography. So in case of electrical impedance tomography, it is again an imaging tool like CT scan. There are array of sensors we have used, and through which we are getting the same pictorial view of our body, just what we are getting through CT scan. So this is for measuring lung twin movement. As we know, in case of COVID, CT scan was very much effective. Similarly, EIT, after development of a proper system, it will be also effective with no hazards, and it is a cost-effective phenomena, and you need not go to laboratories all the time. The sensory system can help you to make picture at the remote, or once the image is ready, you can send it anywhere. Now the second walk I'm going to show you, that is low cost smart CPAP device. CPAP, I think you have heard due to COVID these days, because in case of COVID there is a breathlessness type of thing happens, and CPAP is an low cost mechanical ventilator, handy mechanical ventilator that is available in market, though till now there is no Indian CPAP machine is available. We have to actually import it from outside. But the working principle of CPAP is very, very simple. Here, in case of our CPAP, what we did, the respiratory rate measuring sensor, as I have described earlier, is actually used here for measuring respiration rate. And if there is any abnormality finds, then what will happen? It will ask the controller to drive the busless DC motor. And in case of robotics, we are using, in case of drones, time is limited, so I'm not going towards robotics or drone. There we are using BLDC motor, unlike not the normal motors. BLDC motor is actually busless DC motor. It's having very high speed RPM ratio compared to its weight, and it's busless, so mechanical part is not there. It is electronically controlled. So, and size is also small, so we can make a very handy device for this CPAP type, or medical in dialysis purpose also we can use BLDC motor, etc. And here I'm showing you what will happen. This is the circuitry of this CPAP device. It is not more than 500 rupees cost, because this I got from this hard drive of a scrap computer, and these are the components that I purchased from market. And finally we got patent for this CPAP machine, and now we have a MOU with a company. They are making CPAP, Indian CPAP first time. And here we are actually measuring the monitoring whether the person is getting relief by using CPAP or not. Now we have actually implemented some AI inside it, and there is a lookup table also there that I'm going to show you, that the respiration rate of human being varies with ages. Here, this is the normal breathing pattern of human being between 3 to 12 years. And this is the abnormal breathing pattern between 3 to 12 years. Again, this is normal breathing pattern that is quite different from this between 12 to 50 years. And this is the abnormal for the same age group. This is the normal breathing pattern for persons beyond 50 years, and this is the abnormal. So when we are using this CPAP machine, it is self-calibratory device, self-calibrating type of device. So it can easily understand that for which age group this device is using. And then according to that, it sucks oxygen or air from outside and trying to give relief to the person. So for actually developing this device, we got Best PG Thesis Award from Institute of Smart Structures and System in DRDO Lab Kochi. This is DRDO Lab Kochi. And me, myself, along with my MTech student, Urunava Mitro, got the award. Then wearable activity monitor measuring device. It is again a portable system that's measuring our physical state, but while whether we are walking or running or sitting, sleeping like that. And it is very much essential for working women like us, those who are putting their kids in the creches, to know what my, or with ayahs, what we are willing to know that what our baby is doing now, is walking or sleeping, or in a day, how much time he was running, how much time she was sitting or sleeping like that. At the same time, those who are not staying with their parents, they are also very much anxious that what my parent is doing after 8 hours of sleeping, 8 hours of night. In morning they wake up at time or not, or wake up in time or not. So in that case also, this type of activity detection system is very, very essential. And as we know that as time goes on, the elderly population in our country increases. So this type of system is very, very important. And this is the way of detection, that mechanical pedometer is also there and electronic pedometer is also there. This is the system architecture. There is T-axis MEMS accelerometer we are using here. As we know, we are using gyros in our mobile phones. So when we are flipping the screen, the pin also flips. There are some micro gyros or MEMS gyroscope is there inside our mobile phone. So 3-axis MEMS accelerometer is one shot of gyros. Gyros is used in aeroplanes also to know X, Y, and Z position. Normal accelerometer gives you X, Y position, but X, Y, and Z position is given by gyros. And here, this T-axis accelerometer gives you this type of output. You see, this is for X-axis, this is for Y-axis, this is for Z-axis. And when resting, you see, all the axes are almost deflection is nil. When walking, this is the output. When running, this is the output. So this is the final prototype we have developed. And if you are willing, you will get a paper out of it that came last month, last month, I think, in IEEE transaction, where we are comparing our device with markedly available devices. That is Mi Band, Moto 360 Zen, Google Fit app, and this is our algorithm. Each time it's giving better result. And at the same time, the main attribute of the device is that this is a standalone device. Like when we are wearing Mi Band or Google Fit, then what will happen? We have to use our smartphone with us, because without smartphone we cannot use it. So a smartphone is always required, but we have developed such an algo that it can be used as a standalone low-cost device, and no external device like PC or smartphone is required with it, and it is very, very energy efficient. So it can be again connected with remote by using IoT, and suppose in case of a diabetic patient, doctor at far end can measure how much exercise you have done, and you can also measure whether you have achieved your goal or not. And finally, I am going to show you the smart spoon. That is, we know in case of Parkinson patients, they are facing difficulty while they are having food, or they are while they are serving food like that. So we are trying to develop a steady platform or stabilized platform through which any spoon can be connected. And in spite of the hand tremors, the person is having hand tremors in case of Parkinson. So in spite of the hand tremors, the spoon will stabilize the food. Okay, so this is our invention. This is the stabilizing platform that we have developed, and these are the existing solution, that is heavy weighted cutleries are giving to the Parkinson patients. But the problem is that whether a person, elderly person having hand tremors, he or she even face more difficulties to carry such heavy weighted spoon or heavy weighted knives, whatever you can say. And at the same time, they are facing difficulty while they are having medicine also. So this is our solution. It is easy to adapt and can attach the stabilizing handle with any standard spoon, and it is totally operated by battery, and it is cost effective and open source, both hardware and software we are using, so anybody can use it. So I'm showing you, this is our approach, that we are using again MEMS accelerometer. So first few seconds, it is again self-calibratory type of calibrating type of device, means first few seconds it will actually measure the hand tremors of the patient, and then it will generate tremors in the opposite end so that the spoon will be stabilized. These are the block diagram, and this is circuit of real-time implemented circuitry. You see here actually the spoon will be hidden. So in spite of the hand tremor, it stands still. So these are the main attributes of our smartphone. First one, it is you can wash it. Spoon you can wash. Google is also having, that is very much costly, and the spoon is fitted with the circuitry, so you can't wash it. But in case of ours, you can wash it, and it is battery powered, so no problem of shock or hazard. And both software and hardware are open source, so anybody can use it and anybody can develop it, anybody can maintain it easily. So again, we have used it with IoT, and we can do data analysis and all. So with medicine, Parkinson's medicine, doctor at far end can monitor whether the hand tremors are reducing or at which frequency the hand tremors is going on, like that. So finally, for innovating this smartphone, we got Gandhian Young Technological Innovation Award at 2016. In 2016 at Rashtrapati Bhavan, New Delhi. You see, we are standing here. And finally, I could conclude that sensors along with artificial intelligence always promising are always promising to boost up the industrial robotic system so that the intelligence of the system will be increased. Thank you. I think I have finished in time.
Thank you, Dr. Mobirima Chakraborty, for your valuable and most effective speech we have ever received throughout this evening. So now I will request the participants to raise any questions by switching on their microphone right now. So dear participants, I am requesting you to raise any questions right now if you have any.
We have 1 minute more.
Yeah. So dear participants, I am requesting you to raise any questions right now if you have any, or you can type in the chat box, or the corresponding mail ID of the Dr. Mobirima Chakraborty is there, that is giving in the schedule itself, right? So you can directly mail them, mail
Yes.
her for inquiries, and I think that from this session, that this session is very much up to date and much innovative. that participants may not have any type of question to read out. I think, and everyone is messaging other nice session, nice session, nice session. So, right now I think that everyone is typing very nice session. Everyone.
Okay, thank you, Dr. Karmakar.
Thank you very much for your contribution and presentation. Thank you. Thank you.
Okay, I'm leaving then. Thank you
Okay.
all for listening. Thank you
Thank
for
you.
your patience.
Thank you.